So I want to start with a quote that you begin your new book, Battle of the Big Bang, with. And then I've got a quote to consider side by side. And then I think my question will be obvious. Okay, so your preface begins with a quote from Alan Guth. The Big Bang Theory never was a theory of the bang. It said nothing about what banged, why it banged, or what happened before it banged. Okay, end quote. Let me read you another one. This one from Barrow and Tipler, two fairly famous physicists. In simple models such as the Friedmann universe, the finite length of all time-like curves is caused by an all-encompassing singularity, a finite time in the past. At this singularity, space and time come into existence. Literally nothing existed before this singularity. So, who is right here? What does the Big Bang Theory actually tell us? Does it feature a bang? Does it feature an absolute beginning of so-called singularity or not? We'll start with you, Phil.
Well, the answer is very easy. Alan Guth is right and Barrow and Tipler are not. Okay, so but you don't have to take my word for it. We've actually done surveys of physicists on this very question. What do we mean when we say Big Bang? Because in the book we highlight two different meanings that you could use. So one is what we call the hot Big Bang, and this is the theory that says the universe evolved from a hot dense state. Says nothing at all about whether the universe had a beginning of time or not. It might have, it might not have, but the theory just doesn't say that. The other definition is what we call the Big Bang singularity, and that would imply a beginning of time, and it says pretty much what Barrow and Tipler says. So we surveyed physicists. In fact, we went to this conference in Copenhagen, leading physicists, really big names in the field. And out of 12 questions that we asked them, different controversies within physics, like what's your favorite dark matter candidate? What do you think dark energy is? What's the right interpretation of quantum mechanics? Stuff like that. The only question that we got a majority view on, and in fact it's quite a large majority for sort of controversial issues, was this question of how should we define the Big Bang. And 68% of physicists plump for the Big Bang is the hot Big Bang. It doesn't say anything at all about whether the universe had a beginning or not. And in fact, those that said it had a beginning, I think, was less than 20%. I mean, there were two different beginning categories, one with a singularity, one without. But I had them both up, they were less than 20%. So now that doesn't mean that physicists think the universe didn't have a beginning, but rather it means that when we talk about the Big Bang, we're just talking about this theory that says the universe evolved from a hot dense state. And last thing I'll say on this is that we collaborated with the American Physical Society, and we've done a much bigger survey. It's the largest survey of physicists ever done, I think. And weirdly, really weirdly, the number that supported the hot Big Bang as the right definition of the Big Bang was exactly the same. I think it was 68%. Now, of course, things aren't decided just by surveys. I don't want to just appeal to authority. But in the book, we lay out the reasons why we should only define the Big Bang as the hot Big Bang. And that's what we have the evidence for. That's what we have the empirical evidence for. The singularity is this thing that says time started. And pretty much no one in the field actually trusts that it's real.
Niayesh, did you want to add anything?
Yeah, I just wanted to add, just echo everything that Phil said, and maybe kind of explain a little bit what Barrow and Tipler were thinking about. So, there is a story of a standard Big Bang, which is not the story most people believe now, but it was the story that has been told for decades. And that story starts from a singularity. But it is just a story, and in some sense, it's just an absurdity of what you get if you extrapolate the things that we know about the universe to kind of an absurd point. I don't think it's ever meant to be taken literally, but of course, in lieu of better information, well, in the absence of better information, has been said, this has been written down for decades. But it was never taken to be literally. But I suppose some of my colleagues have been sloppy with their language.
Right. I mean, the question here isn't yet, like, did the universe have a beginning? It's more just a preliminary interpretive one. Like, what does the Big Bang Theory actually assert? And at some level, this is just a semantic dispute. We can still distinguish two models. One is what you call the hot Big Bang, and then the singularity Big Bang. But I do think cosmologists have, at times, they've slid between the two. And so it's not always clear what they mean, because you have that quote from Stephen Hawking in his book, The Nature of Space and Time, where he says that almost everyone now believes that the universe and even time itself had a beginning at the Big Bang. And so whether you agree with that sociological claim or not, it makes you think, oh, the Big Bang, that refers to this absolute beginning in this infinitely dense state. So was there a time when the Big Bang Theory was a model that featured this absolute beginning? Again, it's not that important a dispute. We want to talk about what does the evidence support, not just like what do we call our models. But I can't help but think like people can't be blamed if they're coming to the conclusion that the Big Bang Theory refers to this more metaphysically heavy claim that there was a beginning. Do you see what I mean?
Yeah, I mean, I think it's useful just to distinguish between the sociology and the science, right? So there's a sociological question, like what do scientists mean when they say the Big Bang? What do scientists actually believe?
Right.
Now, when Hawking made that comment, I think that was like 30 years ago.
Yeah.
So they may well have believed the universe had a beginning 30 years ago, but I think things have changed. But the scientific evidence hasn't changed, but that only supports the hot Big Bang.
So maybe I can give another analogy. Like, so there was this atomic model of matter, and I mean, there was ideas of that were around from ancient Greeks, but then we kind of started to have more scientific picture for it in maybe 1800s. Or atoms and molecules and from thermodynamics. But of course, I mean, that was a picture that was successful and it could explain certain things like properties of gases and things like that. But the fact that like an atom is made of electrons and nuclei and then nuclei are made of protons and neutrons. So those were kind of fine details that in these early pictures were just, they're blind to that picture. But then when we understood atoms and molecules better, we realized that, okay, so there are more nuances. They're not just points, they're not these atoms and molecules, which constituents of gases and liquids. So, and the same thing is true with the Big Bang, is that we first got a basic picture, and then we tried to understand it better and study it better, compare it with the evidence, with various theoretical ideas, and the picture got more and more complicated and more complex. And that's basically what happened with the Big Bang. It used to be a simple picture, but kind of the more we studied it and tried to understand it, we realized it's more and more complicated.
Okay. So I've got a question here that is more technical in nature, but I have always been curious about this. And since I have you here, Niayesh, I'm going to ask you. So you'll often hear reference to the Friedman, Lemaitre, Robertson, Walker metric or model. And then at the same time, people will talk about the Lambda-CDM model. So, okay. First of all, those are some complicated words and letters. What do these two things refer to, and how do they map onto the standard model or the Big Bang model? Like, what's the relationship between all these things?
That's excellent questions. And of course, the names of the people you mentioned, Friedman, Lemaitre, Roberts, and Walker, they were just gentlemen who were influential in development of cosmology early on and kind of describe it in the context of Einstein's theory of general relativity. So Lemaitre, famously, he actually argued with Einstein whether his equation, whether Einstein's equation actually predict the universe cannot be static, should be either expanding or shrinking. And he was like one of the first people who actually measured, have good arguments that even observations suggest that the universe is expanding. So these were kind of gentlemen who were very influential early on to understand how kind of universe on very large scales should behave in the context, in the mathematical kind of framework that Einstein developed, which Einstein himself, and of course Einstein invented the equations, but he didn't exactly know what are the right solutions, because I mean his equations admit infinitely many solutions, but what are the right ones for our universe, that was really the thing that wasn't clear. And it required basically collaboration between these gentlemen and many others, observers, that we talk about in our book, to come up with a crisp picture of basically what expansion of the universe looked like. And that's, so this space-time or metric that you mentioned, Friedman, Lemaitre, Robertson, Walker, is basically description, is an idealized mathematical description, but it's a mathematical description of a universe which is completely homogeneous, anisotropic, and everything just changes with time. Okay, there's no other dependence except for time dependence. Now, that's a mathematical description, and I mean, it has very specific assumptions, but it doesn't tell anything about the history of the universe. It just says that there is a history. Things only depend on time, but otherwise it's the same, no matter which way you look at and where you are. Now, the Big Bang story, then kind of description of what the story is, which is basically this realization that if you try to solve Einstein equations, so not in this, with assuming these symmetries, then really there are two possibilities. One is that the universe would be crunching into singularity, or it would be expanding out of a singularity. Basically, there is no static, or there are very kind of fine-tuned static possibilities, but most cases, most generically, you have to be either expanding or collapsing, and there should be either a beginning or an end if you are trying to solve Einstein's equations, basically. So Big Bang is basically a story which is said in or told in the language of Friedman, Lemaitre, Robertson, Walker geometry. So basically, this Friedman, Lemaitre, Robertson, Walker is kind of your character, if you want, you're thinking about the story. And Big Bang, the story, is the story that this character plays, which is basically just the size of the universe is the only thing that is dynamical there. And Big Bang says the size starts from 0, or I should say the density starts from infinity, and then it kind of continues to drop to finite values and so on. So that's these two stories. And then kind of Lambda-CDM is kind of more recent kind of version of this story, where we kind of, in the past 20, 30 years, which is I kind of remember when this was happening. There were kind of various iterations. When I was a student, there was this thing called a standard CDM, which was different. And before that, there was Einstein de Sitter. And there were kind of these variations of, okay, we understand how things started. We think there's something like a Big Bang. There's some hot, dense state. But then, okay, how do they evolve over time? CDM stands for cold dark matter. So it's basically another character that's kind of you have to introduce to tell the full story. Because, I mean, the size of the universe is a story of geometry. So Friedman, Lemaitre, Robertson, Walker tells you the geometry of the universe. But geometry is not necessarily the only thing you care about. You also care about the matter around you. And it turns out there are basically two types of matter other than ordinary matter that we kind of comprehend and can touch, like you and I. There are two other types of matter, or kind of energy if you want, because matter and energy is kind of the same thing. There are these two things that are basically most important, at least for the past 14 billion years or so, let's say past 13 billion years if you want. One is this cold dark matter that constitutes basically most of the density of the universe, at least up until a few billion years ago. And the other is this so-called lambda, which is dark energy. So we call it, lambda is the simplest model of dark energy. So there are two additional components that basically for the past 13.8 billion years have driven the expansion of the universe, have driven the show. And these characters is dark matter and dark energy. And what Lambda-CDM means is basically in the past 20 years, we realized that these are the two things that are most important to drive cosmic dynamics.
Well, if you think of it like a detective story, you've got these characters, and usually one of the characters, or at least one of the characters, maybe more, aren't what they seem. So I think the same may be true in this sort of Lambda-CDM story. So we were often told, okay, the dark matter is this cold dark matter, it's a new particle probably, and then lambda is a cosmological constant. But there's a bit more dispute about that than some cosmologists would have you think. So we don't know for sure that the dark energy is a constant. There has been some empirical evidence coming from something called DESI, implying that it's not a cosmological constant, that it changes over time. Now, you want to be very cautious when new evidence like that comes along. More than likely, whenever you see an exciting new discovery in physics, it's probably going to go away and turn out not to be real. But, at the moment, it's unclear for sure whether dark energy is a constant and whether dark matter is, a new particle. It could be many different things, actually. It could be a new particle and something else. But now these might affect the fate of the universe, particularly dark energy. Depending on what you think about dark energy, it would affect the fate of the universe. But it wouldn't really affect whether, the hot Big Bang happened. So don't get worried too much about Lambda-CDM if you're concerned about whether the hot Big Bang happened or whether there was a Big Bang singularity. But it might affect whether, there was a cyclic universe or what type of cyclic universe, because some types of cyclic universe require a cosmological constant, other types require it to be changing. So that may impact kind of which model of the Big Bang you think about.
So, go ahead.
So I think maybe just a simple way to summarize all of this is that if you think about the story of cosmology, the story of universe as some sort of kind of thing, it's kind of fuzzy and we start to understand it better. So Friedman, Lemaitre, Robertson, Walker is like the language we use to describe this. The Big Bang story, the story of the beginning, and Lambda-CDM is the story of the end. And they are all kind of stories that are under development and can get more and more complete, the better understand what's going on.
Okay. So there's a sense, and correct me if I'm wrong, in which FLRW spacetimes, they're like a class of models that meet certain features, that all share certain features. And then Lambda-CDM is a specific model within that broader category, a specific model of the universe. Is that one way of drawing the distinction?
Well, as I said, so it's the language versus and the story, right? So let's say we're speaking English. So this is the language we decided to speak in. And FLRW is the language that you describe a universe which is homogeneous. So that's the language. Now, Lambda-CDM is indeed the story that we tell. So it's what actually we're talking about. The specific story is the Lambda-CDM. And of course, it doesn't have to be the final story. The story, as Phil mentioned, if you understand the universe better, there would basically more nuances and more wrinkles in the story that we understand.
Mm-hmm. And the Lambda-CDM story, is that the same thing as what you're calling the hot Big Bang, that the universe began in a hot, dense state and has since evolved to the present day? Are those the same thing?
Well, no, so I was saying, so Lambda-CDM is kind of the end of the story, and hot Big Bang is the beginning of the story, right? Okay. And of course, you want to kind of, at some point, you want to match them together, and we have ways of matching them. But really, Lambda-CDM are the main characters at the end, which is the past few billion years. And hot Big Bang is what happened when the universe was basically younger than 400,000 years old, something like that. So at that point, basically, you have photons and neutrinos really dominated the density of the universe. And as you go earlier and earlier, then you have other characters that show up. And Lambda and CDM don't really play a role, at least not the Lambda and CDM that we know, the dark matter and dark energy that we know. There are other characters that come about, and the closer you get to this quote-unquote singularity, there could be newer and newer characters that show up, which may or may not get rid of singularity, basically.
Yeah, you'll have to forgive me for hampering on terms so much, but like this is the stuff philosophers love, is to zero in on key terms and go, but what does it mean? So thank you. All right, so throughout your book, you talk about the need for models to resolve the singularity. At a few different points, you say, this is problematic because it doesn't resolve the singularity. I take that to mean this model doesn't yet show that there are no singularities, remove the singularities, whatever. What's the motivation for claiming that a model needs to resolve the singularities? Is a singularity physically possible? Is that something that science could verify? So why do we need a model to do away with singularities? So if you could speak to that, either Phil or Niayesh, whoever.
Well, I think actually Niayesh hosted a conference at the Perimeter Institute for Theoretical Physics, which I was at, and there was some philosophers there talking about this very topic. Well, what's the problem with singularities?
There we go.
Why can't we just accept them as real? And I think the thing that they objected to, this is what the best argument, I mean, there are various arguments, probably the best two are, one is what we call loss of predictivity. So you can't predict anything if you have a singularity. So now you could say maybe nature doesn't care whether we can predict stuff, so who cares? That's one way, but obviously it's unsatisfactory if you can't check your theories, because your theories need to make predictions to be sure that they're right. So if you can't predict anything, then we can't be sure that they're right. So that's one issue. But I think the bigger one is the idea that general relativity and quantum mechanics contradict each other. Philosophers generally don't like contradictions, and you're basically assuming general relativity in these singularity theorems, and you're not using quantum mechanics. So for those that don't know, general relativity is the physics of very big stuff, if you like. Quantum mechanics is the physics of very small stuff. And for the most part, the fact they contradict each other doesn't matter, because they're at such different scales, who cares? But when you get to the Big Bang, the hot Big Bang, you're getting to higher and higher and higher energy densities. And at some point, we think that quantum effects will kick in. And then you've got two theories that are needed and contradict each other. So that's a problem. Now, the third issue is with infinity. Now, I think there's some tricky issues. So you might say, well, if you remove a singularity, you've got the infinite density, infinite curvature, infinite pressure, infinite temperature. And you might say, well, that's unsatisfactory. But then if you remove them, maybe the universe always existed. Then you've got another infinity, right? So maybe you have to choose which infinity you like. But I think one distinction to be made is infinities that you couldn't measure if you had some measuring device. So if you could go back to the Big Bang and you could measure the density and it reads infinity, that's a problem, because you can't, infinity isn't really a number in that sense. Whereas if the universe had stretched back forever into the past, you'd never measure it, right? So for any observable, you can't have infinite values. For non-observables, like whether the universe is infinitely big or infinite in time, well, you wouldn't have any kind of measuring device that would measure that. So maybe those infinities are sort of okay, and the others are not okay. Does that make sense?
Yeah, that does. I think that's very interesting. I wonder with that second point that, it is true. The singularity theorems assume that general relativity holds and general relativity breaks down very close to the Big Bang. And so perhaps in a quantum theory of gravity, we'll have a universe without singularities. But I guess my question pertained to something a little different. Whereas I interpreted you in the book to mean that we don't want our future models of the universe to feature singularities at all. And so it's a virtue of a model if it doesn't have a singularity. And I guess my question is, well, who's to say whether a quantum theory of gravity won't include a singularity? Maybe our best model of the universe based on quantum gravity will also have one. And is that necessarily a bad thing? Now obviously, one isn't saying here that we have grounds for thinking there is a singularity. I'm just wondering if it's possible that a model with quantum gravity, with a true theory of quantum gravity, will also have a singularity, and how could we know that it wouldn't? You see kind of what that question is?
If I can follow up, yeah. I mean, absolutely. No, this is perfectly fine. So really, I mean, it's not that we are allergic to singularities or anything. I mean, they can live as they wish. Very open-minded people. But the real question is this predictivity. Okay. And in fact, it's predictivity not just in the case of classical general relativity, but rather quantum gravity. So really, well, even if only we have general relativity and then there were these singularities, maybe I would be happy with them. But the problem is we have quantum mechanics as well. And quantum mechanics when we approach the singularities is when, any singularity, is exactly when we know we cannot trust classical general relativity anymore, and quantum effects basically get out of control. So now, if we can consistently kind of include a theory of quantum gravity, or possibly quantize general relativity, although I think most people have given up on that, but if we can have a consistent theory of quantum gravity, it should kick in near the singularity, and it should give us some predictive behavior, something that we could test in principle somehow. Now, whatever that is, it wouldn't probably have language of general relativity, so what a singularity is in that case is not even clear. Like if you have a strings or you have loop quantum gravity, you would have graphs and discrete space-time. So it's not even clear that the language of quantum gravity, and we have many ideas for quantum gravity that we kind of go over in our book. It's not even clear that singularity belongs in that kind of basically terminology, because we're not talking about a space-time anymore. We're talking about other things. But I mean, if the theory is not predictive, then it's lacking something. And kind of the enterprise of physicists has been to kind of have more and more predictive theories. If the theory fails at some point, then we would think, okay, so maybe you need completion. Maybe there's a better theory. And that's kind of the idea, right? We kind of had a flat Earth theory that's kind of extended to some point, and then we realized, okay, no, maybe Earth is curved, and then we had a theory of the solar system where Earth was the center, and then we kind of understood it better and better over time. So this is really part of the same kind of history, same legacy, that singularity, it's not that we have anything against the singularity, we just want to understand our universe better and better, and where our theories lose predictivity, then we think that there must be like a more comprehensive, more all-encompassing theory that could push us further.
Right. Okay. Let me ask you about the so-called singularity theorems in that case. Many people will point to the Hawking-Penrose singularity theorems as the pretty ironclad evidence that you can't avoid a singularity. So long as your model of the universe meets certain conditions, you're going to have a singularity. I think the selling point, or the main attraction of it, is that they don't assume the universe is homogeneous or isotropic. Correct me if I'm wrong. And they still show you can't avoid this initial space-time boundary. Why aren't those singularity theorems as powerful as people seem to claim? And there are other theorems, and we'll talk about those, but we'll start with these.
Right, so in our book, we lay out sort of 4 assumptions that the singularity theorem has. Do you want to go for all 4, or
Sure.
just pick the best one?
Sure.
All 4? All right, okay. All right, so the 4 are, one is what's called an energy condition, but you can think of it as just whether gravity is always attractive or not. So now you might think, well, gravity is always attractive. When I throw a ball up, it comes back down. You don't see it flying off into space when I throw a tennis ball up. But it turns out that you can have negative gravity, and in fact, the standard model of cosmology, Lambda-CDM, has negative gravity. That's dark energy. So dark energy is basically negative gravity. There's also this theory called inflationary cosmology, and that also has negative gravity in it. So that assumption looks wrong. I mean, just empirically wrong. The second one is that we have 3 dimensions of space and 1 dimension of time, and you can measure with rulers and clocks. So you can challenge that as well. You know, maybe there are more than 3 space dimensions or more than 1 time dimension, or maybe you can't build rulers or clocks in some extreme conditions, or maybe you lose a dimension. So you can challenge that. The other one is basically that time travel into the past is not possible. Well, I mean, it's certainly a challenging thing to accomplish, but it's not agreed upon that it's ruled out by our current physics. So there are solutions that people have found to Einstein's equations that allow time travel into the past. But the last one, I think, is the one that most people focus on, that general relativity is our theory of gravity, and it's going to be applicable at all scales. Well, it's applicable at most scales, certainly any scales that we've tested, but there's an enormous range of scales that we haven't tested. And when we get to this Big Bang, most people think that the quantum effects are going to kick in. So you might not even have space-time anymore when you would get to a quantum description. So, you know, who cares what happens to space-time, because you're not even dealing with space-time anymore. Or maybe you are, and you can extend the space-time beyond the singularity. I mean, one way I like to think about it, I think it was Anthony Aguirre that said this, but I might be wrong, who said, all a singularity theorem can really tell you is that the space-time that obeys the condition of the theorem is, let's say, past incomplete. It has a beginning. But there could be another space-time that doesn't obey the condition of the theorem.
Right.
So all theorems have to have physical assumptions. You can't have a physical theory without physical assumptions. So it could be that, yeah, the universe stops existing at the singularity. Maybe that's true. But an alternative is there's just another space-time beyond that doesn't obey the condition of the theorem.
Right. Phil, Niayesh, anything?
Yeah, absolutely. And I mean, I think, again, as I was saying, in the past 40, 50 years, we understood these conditions kind of better and better in various contexts, and kind of came up with all these examples of where they do break down and where they should break down. And indeed, that is the story. That yes, there could be things as we, in the most conservative sense, they would break down at some point, and that would be a singularity. But if you kind of open up the space of possibilities, there could be kind of other degrees of freedom that show up. I mean, one way to think about it is like, if you understand you have a theory for water, right? So describe how water flows in the river. But then at some point, water may evaporate. Maybe you heat a hot surface and then it evaporates. And your theory ends there. That doesn't mean that there is no water. I mean, there's no other theory. There's a theory for the vapor, right? Or water molecules. And that's kind of the Big Bang, or the singularity could be something like that, is that these equations that you had for liquid water, which in our case would be general relativity, continuous space-time, classical general relativity, that just stops making sense at that point, but there is some other more complete theory that kicks in.
I would just add, actually, Miles, that there are other cases where you get singularities or analogies to singularities in physics. Like fluid flows, you can get infinite instability, or models of the atom where the electron spirals into the center because it emits an infinite amount of energy. And generally, they're just taken to mean your theory is broken down, so you need a better theory, rather than physics is broken down.
I think that's an important point. And perhaps that speaks to why singularities specifically seem antithetical to like scientific investigation. It's not just the concept of a beginning to the universe, but it's a very specific kind where things become infinite. Maybe that's what is problematic for the reasons you've kind of outlined. That what could we actually... Well, first of all, one thing that it seems problematic to me is if there really was this actual state t equals 0 where these quantities are infinite, we're then to imagine that they become finite a finite time later. And how do you go from an infinite density like down to something finite? That seems metaphysically suspect. I mean, that's kind of some of the issues you were bringing up, but that has always seemed odd to me, is like, how do you go from a state that's actually infinite to one that's finite? Maybe that's possible, but there's this strong intuition that how do you climb down from infinity, so to speak? Does that kind of make sense?
Yeah, I mean, people have talked about, whether the universe could be infinite in the past, and they often object to this because you can't get to infinity. But that always assumes like a starting point, and I think that's just the wrong way to think about it. If the universe was infinite in the past, it didn't have a starting point. However, you could use the same argument with these singularities and say, well, you'd have to count down from infinity to some finite value. How do you do that? That's no less problematic. In fact, I'd say it's probably more problematic.
Yeah, it seems more problematic. Well, all right. What about newer singularity theorems, if it's even right to call them that? And here I have the infamous Borde-Guth-Vilenkin theorem in mind. Now, I don't know if you had a chance to watch my interview with the philosopher of physics, Tim Maudlin. It was fun and it was good. It featured a very unique moment for me as an interviewer where I brought up this theorem and he immediately lost his mind. So I ask you two not to, because I don't know how to handle that kind of reaction. But what do we think about the significance of the Borde-Guth-Vilenkin theorem? I'll leave the details to you to sketch because I think I'd flub them. But the basic idea is that any model of the universe that features the universe as on average expanding throughout its history, so on average having positive expansion, cannot be past complete. It must be past incomplete, which I take to mean it must have an absolute beginning. And what makes... Now I'm going to sound like William Lane Craig. What makes this theorem so powerful is that ostensibly there's only one assumption behind it. So long as your space-time meets that one condition, that one assumption of average positive expansion, then no matter what else might feature in your theory or model, like quantum gravity theory or any other bizarre conditions, we know that there must be a beginning in that model. So, do we now have a powerful singularity theorem that can circumvent the issues you've raised for the Hawking-Penrose singularity theorems? There's now just one assumption, which is apparently pretty plausible, and so it must be that the universe had a beginning. We'll go with you, Niayesh, to start.
I mean, it is a very powerful theorem, but it's also just as powerful as this assumption, which is universe has been expanding throughout its history, and of course it didn't have to. And I think that's really, in some sense, I mean, it's like 2 pages, like half a page of mathematical derivation. So it's kind of almost too good to be true. And really, if you kind of read through it, it's too good to be true. It's just, I mean, this idea that universe has been expanding all the way through, that's, of course, I mean, you could assume that, and it says there must have been a beginning, but of course, it could be that the average expansion was 0 throughout the history. It could be that universe was contracting at some point. And of course, it could be that the idea of the size of a universe, a classical description of this Friedman-Lambert-Robertson-Walker universe that we discussed about, FLRW, that may break down at some point. So, I mean, the problem with this is that the counter example to this theorem already stares you in the face. I mean, if you have just an inflationary universe with the curvature, it collapses and then expands, and there's nothing wrong with it. And so of course, it's infinite to the past, except that if you go back in time, it's not expanding, it's contracting. So that's the counterexample. And clearly, I mean, where the contraction becomes expansion, it's not a singularity. It's just where contraction becomes expansion is the bounds. So it's so I don't know. It's powerful, but it's kind of also benign, in my view.
Phil?
Yeah, well, I'd add maybe a little bit of historical context to what this theorem is really about, because the idea was that inflationary cosmology is eternal. So once it starts, it never stops. So there's a natural question to say, well, if it's eternal into the future, is it eternal into the past? Right, so this theorem basically was trying to address that question. Well, if inflation is eternal into the future, is it eternal into the past? And the conclusion is no, inflation is not eternal into the past. Okay, that's very interesting. That is very interesting. Okay, does it prove the universe had a beginning? No, of course it doesn't, right? It just says inflation has a beginning. Could there be something before inflation, like a contracting universe, assuming inflation happened? Yeah, of course. And of course, it's also possible that inflation didn't happen at all, in which case, who cares whether inflation has a beginning or not? You know, the other thing is to say is also that recently there's been some work doubting the Borde-Guth-Vilenkin theorem. So there's a paper by Lesniewski, Essen, and Davis said actually the theorem is mathematically wrong. Now, of course, people make claims back and forth. I don't know who's right and who's wrong here. What we do want to do is when we become really confident in a conclusion, it's because there's empirical evidence for it. So when theorists are disputing these things, and they do dispute them, I say, you know, let's be a little bit more humble and say, wait for empirical evidence. And unfortunately, the chances of empirical evidence coming in and ruling out whether inflation is eternal into the past and the future or just into the future, I can't see any prospect for that. So why are people so confident about this conclusion? You know, we should be confident about conclusions that are empirically well supported. And this is in a realm that empiricism is kind of hard to touch. So I would say be more cautious about this. So even the very and also I think there are other assumptions that are not mentioned. Space-time is classical. You have to assume that. Also, I think the speed of light is a constant, can't be breached. I think that's when you interviewed Tim Maudlin, if I remember.
Yeah, that's what he said.
Correctly, he was like, well, I don't believe that. Tim Maudlin doesn't think it's true that the speed of light can't be breached.
Yes.
And there is the theorem that we talk about, quantum gravity theory we talk about in the book called Hawking-Penrose gravity. And this would imply that the speed of light goes up as you approach a singularity and will become infinite. In which case, I'm not sure that Borde-Guth-Vilenkin would actually work in that approach, because they do assume that the whole point of it is you're looking at these particles and how they measure their speeds, and as you go back in time in an expanding universe, the speed will approach the speed of light, and you can't go faster than the speed of light. Well, that's true in standard relativity, yes, but in Hawking-Penrose gravity, it's not true. So I think there's more than one assumption actually.
That seems right to me, that there isn't just this single assumption. In particular, let's say more about this assumption of classical space-time. And what does that mean? What is the assumption of classical space-time? And what's a model of the universe that does not feature this assumption? And we'll go Niayesh if you want to.
Yeah. So I actually just coming back to the point Phil was mentioning is, I mean, can we test the beginning of inflation? And in some sense, it is. I mean, it's not. There's no guarantee, but I can imagine situations where you can test the beginning of inflation. And like there were, one idea is that if you have in eternal inflation, you have bubbles. I mean, you have pocket universes that pop out of here and there, and inside each of them there is one universe. And depending on how long inflation lasts, we could actually see signatures of the beginning, maybe in larger scale in cosmic microwave background. So I mean, I think it's not crazy to think that if there was a beginning, we could test it, but I don't think there's any guarantee that we could test it, because if the inflation lasts a very long time, it would be hard to see it. Now, the question of this classical space-time. So basically, Einstein's theory of relativity, or general relativity, I should say, is based on this premise that gravity is really, it's not a force, but rather geometry of a space-time. So there is kind of a language. So Einstein gave us, maybe Einstein's greatest gift to humanity was this language to describe a space and time. So he thought that basically a space and time are endowed with a geometry. And this geometry is universal. Everybody sees the same geometry, and that's kind of that's why the feather and hammer fall together, because everybody sees the same geometry. The geometry is universal, and that's an assumption which is very powerful, but also very classical, because I mean, if this geometry starts to, I mean. Also, Einstein predicted that this geometry is dynamical, so have gravitational waves. So, I mean, when things move around, they emit waves. So they have their own oscillations and life and death. Well, these waves go around, waves of geometry. So if you start applying rules of quantum mechanics to this geometry, then things become different, and basically this quantum geometry wouldn't necessarily react the same way when it kind of sees a feather and a hammer, sort of speak. So the equivalence principle, if you want, doesn't need to survive quantum in quantum gravity, and that's kind of the same thing as saying that a speed of light may not be a fundamental limit, right? Because really, the speed of light being fundamental limit is something that's almost equivalent to saying that there is a universal geometry. But if there is no universal geometry, different objects could see different geometries, for example. Then there is no finite speed of light. There could be different speeds of light for different things, or depending on the energy, energetic particle may go faster, may experience a faster speed of light than less energetic particle. So that's kind of the idea, is that this idea of a universal classical space-time that everybody experiences the same way, at the quantum level, that may evaporate, and different things may experience different classical space-time, different geometries, or no geometry at all. They're just going to talk to each other in kind of more complicated way. So we don't all experience or talk to each other through kind of living in this geometry, but rather in some more complex way. It's kind of thinking that, I mean, it's an imperfect analogy, but like imagine if you're somewhere that's clear and there's no fog, and then you can see everything, but then when it gets foggy, then you don't really see what's going on around you, and so light doesn't propagate on a straight line. And it's kind of the same idea that the geometry, it's kind of, when the geometry becomes very quantum, then you cannot really talk about everybody kind of being on the same page on where they're moving and what they're doing.
Phil, did you have anything?
No, I think what Niayesh said is spot on, yeah.
Yeah, I guess what I wanted to get your thoughts on is this idea that space and time might be emergent realities. This is an idea that's thrown around here and there, that space-time is emergent. It emerges in some sense from a non-spatiotemporal structure. Now, the challenge is making that claim mean something coherent, showing that that claim isn't just incoherent, because there's an obvious sense in which emergence of time doesn't make any sense, and that's emergence over time, like the slow development of something into something else. Development in that sense is a temporal notion. So you can't have time itself develop over a temporal interval of time. So what at base do physicists or cosmologists mean when they say that space-time might be emergent? Obviously, it's going to be very hard for you to explain this in a way that someone without the technical background will understand, but I'll give you the chance to try, Niayesh or Phil.
Oh, okay, sure. Okay, so I think the idea is that it's underlying from a quantum, some kind of quantum state that doesn't have time in it, or space and time in it, depending on which theory you tackle. So some of them say that maybe time is emergent. Some of them say, actually fundamental. I mean, there are different theories. As to this notion of, well, how could it emerge if there's no time? Why doesn't it just stay as it is if there's no time? How could it possibly develop if there's no time? So the way I try and conceptualize this in my head is to think of time as something periodic. One physicist said to me, time requires a correlation between events. So you could have events that aren't correlated, and then things are actually happening, but there's no time because you don't have anything periodic, you don't have any correlations. And then, when I was a student, I used to plot out correlation functions between things, and they have different values, right? You can have something that's perfectly correlated and something that's barely correlated. So you could imagine something becoming more correlated and then, in another sense, becoming more periodic. And then time starts ticking. So I think it's perfectly coherent to say that time is emergent in the same sense that something, can become periodic that wasn't periodic, or could be correlated that wasn't correlated.
Niayesh?
Yeah, I mean, I think it's an excellent question that, can we make this a coherent idea? And I think right now it's wishful thinking. Not to say that it's hard or impossible, it's just saying that we're far from having a coherent idea or coherent theory of emergent time or a space. When I think about this, and to be honest, this is something I do think about every now and then. So what we want to describe the universe is basically a series of observations. So, our experience of the universe, my experience, your experience, everyone's experience, are a series of kind of things we notice, we measure. And then the fact that we give temporal orders to them, so I can give temporal orders to things that I see. So there are basically two things, that somehow I have some notion of what comes of one observation coming after another observation. And another is, I guess, there is something in common with what I observe and what you observe. And they're not exactly the same thing, but there are some commonalities that we see the same thing. Probably, otherwise, if we kind of heard and said different things, then we wouldn't be able to talk to each other. So, so somehow out of this time might emerge. So somehow these experiences, we attach a temporal order to them. But at the fundamental level, maybe these don't exist, and it's a way for us to organize things, kind of like a library that we have an indexing system. There are all these different books that they're all on random things, but we have a way of putting them like in some order. And somehow we all agreed upon this. Why we all agree that there is one temporal order, I don't know, but that's kind of part of the mystery. Again, I think it's the wishful thinking at this point that there will be a coherent idea either for emergence of time or a space. We're not there yet, but that's really, in some sense, the end goal of the program of quantum gravity is that there is something more fundamental than the classical notions of a space-time that we have, and whether in that more fundamental picture, any of the things we talk about today, space-time, geometry, causality, you name it, everything we talk about today, if any of them, even quantum mechanics that exist at that fundamental theory, we don't know yet.
It does, from the outside looking in, look like an impossible goal, trying to formulate a theory to explain that does not itself rely upon notions of time or space or causality. Like, what are you left with? Seems like you've just done away with like all of the fundamental stuff that you use to construct a model or an idea or a universe. it's very hard to understand how you could have anything left to build with, to build a model. That doesn't mean it can't be done. And I'm vastly ignorant of that sphere of cosmology. It from a philosopher's vantage point, it just seems like these are conceptual bedrocks in the way people think and make sense of things. Like how do you get outside that? If that kind of makes sense.
But I mean, the way I think about it, these are all the things that were built by humans at some point. Like we were not, I mean, the clocks and rulers and all the distance measures, these are all the things that we invented at some point. And then of course we built theories based on them. So I don't know. I mean, I think this has certainly been very successful. The whole physical enterprise of physics, quantum mechanics, general relativity. So there are all these things that are used and common between them, but they're all things that we invented at some point. I mean, it was great that of course, we had guidance from the nature, but we all invented these. And if there was a different civilization that developed somewhere else in the universe, they could have come up with different concepts. And I don't know. I mean, I think that the only thing that's fundamental is the fact that we make observations of the world, and there are correlations between these observations. I think that's really the only thing we know fundamentally exists, is that we make observations and there are correlations between these observations. But anything beyond that, to me, it seems that they are kind of made up. They're inventions. They're very, very good inventions, like the supersonic airplanes, if you want. But they're still inventions that are made by humans.
I would add that I think what physics has taught us in the 20th century in particular is that the notions that you get from your experience are not necessarily what we get at the more fundamental level of reality. So these notions of space, time, causality, things like that, they're all what we experience in our day-to-day lives. And and we've got grasp of these because evolution has given us the ability to grasp these. There was no reason for evolution to sort of give us an intuitive feel of the quantum world, for example. So it's no surprise that it feels very strange to us. But it can be written down mathematically, and ultimately that's what we want. These are still works in progress. People are working on this. The idea is space and time are emergent, and people don't agree, and this is the frontier of physics. So, but I wouldn't expect it to follow whatever the theory that we actually develop and finally is agreed upon, and hopefully experimentally tested. I wouldn't expect it to have the familiar notions that I get from my day-to-day life. Physics has taught us that that's not to be expected.
All right, continuing this attempt to construct really general theorems to show that any reasonable model of the universe, it's got to have a beginning. I mean, I think the selling point of this strategy is that it seemingly allows you to sidestep the issue of constructing a model of the universe that has a beginning and then arguing in favor of that model. Like if you can show that all models that meet a very general condition which plausibly holds require a beginning, then perhaps that gives you good reason to think that there is a beginning to the universe. And now we'll talk about that strategy. But last of these theorems I want to get your comment on is Aaron Wall's generalized second law of thermodynamics. Now, I don't know anything about it. All I know is that in William Lane Craig's debate with Sean Carroll, Craig mentioned this theorem and said it's got this fantastic implication that we can generalize the second law of thermodynamics in such a way, with such general concepts and terms, that it's probably going to hold under a quantum theory of gravity, and that generalized second law implies a singularity. So I think it's someone referred to this as a singularity theorem. So there you go. There's a big family of related claims. Niayesh, what do we take of the generalized second law of thermodynamics?
Yeah, so the generalized second law is basically the idea is can we think about entropy? So we think, matter has entropy. That's what thermodynamics has taught us. And then there's also this idea of black holes have entropy. So maybe then we should just add up those entropies, and then they say that those the sum of those entropies should increase. So basically just putting those together, the entropy of the black holes and the entropy of a matter added together. And The issue with it is that it's the semi-classical description, or basically it's still based on a classical notion of a space-time. The reason I call it semi-classical is that you kind of stop things at the horizons of black holes, or horizons, if there are horizons, so places where you need to go faster than the speed of light to be able to cross them. And there are cosmological horizons and there are black hole horizons. So in cosmology is like a black hole inside out. So if you go far away, say in a universe which has dark energy, then it's like falling into a black hole, but they're surrounded by a horizon. So, and then you associate entropy to these horizons. But the issue is that you're still talking about classical geometry here, right? And then there are these energy conditions still, that, remember, energy condition was something you need in singularity theorems. And I think, if I remember correctly, you also need energy conditions to prove a singularity in the context of this generalized second law. And now those energy conditions can be violated. I don't remember which energy condition, but generally all energy conditions can be violated. Defining these energy conditions requires a notion of classical space-time, because they are kind of some sort of average property of energy in a fixed geometry. But if you have wide quantum fluctuations in the geometry, you cannot even define this. So I think they're the same type of objections that I would have. Of course, it's newer, brand new. Whatever is new, people are more excited about it, and it has fancier names and fancier languages. But at the end, it's the same story. And I mean, all the same counterexamples that we had that avoid singularity theorems, they still apply to this as well.
Phil, did you have anything?
Yeah, a couple of things. I mean, the Wall theorem, as far as I recall, requires space to be infinitely big. So William Lane Craig doesn't think infinities are allowed in nature. So I found it really weird that he would appeal to this theorem. The other thing I would say is that in the paper, in the Wall's paper, I remember he was saying something like, maybe this might imply there's a quantum singularity. And maybe it does, but maybe it doesn't. People have different intuitions about that. And when there was some discussion between Wall and Carroll post-debate, Wall made this comment, well, this is quantum gravity, so none of us know what we're talking about. And I think that's the important part, right?
That is
you can
relevant.
have different expectations. People have different intuitions about this. Carroll and Wall are both expert physicists, right? And they have different intuitions about what we might expect. And that's fine, that's okay. But we shouldn't make. But when William Lane Craig is debating Sean Carroll, he's talking to the public and he's representing, what's established science. So it's okay, yes, I think, for Aaron Wall to come out saying my intuition is, quantum gravity theory will still have a singularity. That's okay, right? But when you're talking to the public and you say this is what's established, and you say there's this theorem that proves that quantum gravity implies singularity, you're like, that's really dodgy.
Yes. Your mention of that reminded me of a theorem that Sean Carroll points to kind of balance out on the other side this appeal to theorems, the quantum eternity theorem. I think he did so rather cavalierly and self-consciously aware of the fact that the theorem doesn't actually have this implication that the universe is eternal. But it is intriguing, this idea that we have this theorem where the time variable apparently ranges from past infinity to future infinity. What's the significance of this theorem? I mean, the name quantum eternity theorem is pretty cool. So what does it signify, Niayesh?
I think I looked at it at some point, but I forgot what it was. Phil, do you remember?
I think it's basically the idea that if the universe doesn't have zero net energy, then it must obey the Schrödinger equation. Its time must go from minus infinity to plus infinity. And I think Carroll said in the debate, well, you can easily evade the theorem by just assuming that the universe does have zero net energy, which it might have, And in fact, many models of quantum cosmology, the early versions, particularly like the Hartle-Hawking model and the Vilenkin tunneling from nothing model, I think they assume that the universe does have zero net energy, so it's like a closed universe. But if it doesn't, then it would necessarily be eternal in both directions of time. So I think I think Carroll was being a little bit sort of like a sort of parody argument. It's like, well,
Right.
look, you can pick that theorem and you'll prove the universe had a beginning, or you can pick a different thing, make a different assumption, and you can show the universe doesn't have a beginning. So take your pick, you know. And unfortunately, we don't know which one of those assumptions is right.
If I may add, I mean, it's kind of, I mean, all of these theorems in some sense are very trivial and also very trivially can be violated. But I mean, the thing with quantum mechanics that there's really no singularity in quantum mechanics. If you just take a quantum theory with some Hamiltonian, it's just basically some matrix. It's basically what derives the dynamics. I mean, there's nothing like a singularity that ever comes out of that. It's just you have some simple evolution, you're solving some ordinary differential equations. There's nothing ever goes wrong because the linear equations always have solutions, basically. They're just basically oscillatory solutions. So in that sense, I mean, there is no way you can get singularity. So that's why most people, basically, when they see singularities anywhere, they think because you're not actually doing the quantum thing right. Because generally, quantum theory is just the theory of matrices and solving linear equations that they always can kind of solve them. So yeah, I mean, I think that's maybe, yeah, that's the point, is that the quantum theory as we know it doesn't have singularities. Now, of course, quantum theory may not be complete. But yeah, so that gives you, yeah, the counterexample that any theory, any theorem has its own assumptions, and of course those assumptions fail, the theorem fails.
So we've been operating kind of at the global level, at this big picture assessment of models as a whole using theorems, like trying to rule out whole classes of models without considering the nitty-gritty details. So let me ask you briefly about, in the book you outline 4 like string-theoretic models of the universe: the string gas cosmology, an emergent universe, a pre-Big Bang scenario, and the ekpyrotic universe. And I'm curious how it is you can have a situation where this one single theory gives us at least 4, if not more, like mutually inconsistent models of the universe. I mean, from a philosopher of science perspective, I'm curious, like, what's the relationship between a theory and a model? And I mean, even you yourself, or both of you, wrote that on page 125, the fact that string theory gives rise to these 4 models leaves me perplexed. And it leaves me perplexed too. So how can you get these contradictory pictures all emerging from string theory? Like, what does that signify? What does that tell us about string theory? There you go. Niayesh or Phil?
Well, I think the simple answer is string theory is a work in progress, right? Nobody thinks it's a final theory, right? So people create what are called toy models, where you kind of make some simplifying assumptions, and you take some of the principles that string theory, like string theory gives you new principles, new symmetries. So what people try and do is like, well, let's take some of those ideas and try and model the Big Bang with them. So the ekpyrotic model initially was inspired by the idea that string theory it's not just a theory of strings, that there are other objects, if you like, these high dimensional membranes. So the way that model came about was, well, there was a lecture given by Burt over at a conference in Cambridge, and they said, well, these brains have to be partnered. They can't just exist by themselves. And then it was like, well, what would happen if they collided? You know, and oh, well, there'd be a lot of energy coming out. Oh, that sounds like the Big Bang. You know, so that's what's going on here. You've got different principles. So like string gas cosmology and the pre-Big Bang were inspired by this principle called target space duality. I'm not going to bore you with what that is, but bottom line is it's a new principle, and you get new physics coming out of it. And so these are basically simplified sort of toy models, and given that string theory is incomplete and a work in progress, and then I don't think it's like too surprising that there are different ideas coming out of it. You know, maybe, you know, string theory is ever like finished, and we write down like the basic equations of string theory, which you don't even have at the moment, then maybe one model will come out of that, or you'll be able to say, you know, or this principle is valid, or so on and so forth. So I think that's what's going on there. Basically 2 things. One, string theory is incomplete, and these are basically toy models with a lot of simplifications. And their idea is, well, let's see, you know, if we play around with these ideas, what do we actually get? And you've got to remember, this is a work in progress. So it's nothing like sort of established physics. But this is what happens when we're at the frontier.
Niayesh?
Yeah, I mean, I think certainly what Phil said is that, I mean, the fact that the string theory is not really a complete theory, and some may argue it's not even a theory. It's that's a problem, or that's a hindrance. But even if, I mean, the situations where we do have the rules, we like formation of the solar system or our galaxy, right? So those are, I mean, we think we understand most of what's happening. We know we have the rules, but still we don't have a complete story. And I mean, just because those are two different things, right? So having the rules of the game doesn't mean that you know what the story is, because that depends on what is the right initial conditions, and we don't know what the right initial conditions are. So ultimately, I mean, even if you had a perfect complete string theory, then you should have like considered various scenarios and come up with predictions that came out of that scenario and compare those predictions with observations. And then that would narrow down the possibilities, but it still wouldn't have necessarily given us a unique possibility because, yeah, I mean, universe is complicated and observations are always incomplete. So there could have been many scenarios. Even if you had the perfect theory, there could have been many scenarios that are consistent with observations. So yeah, so this is the nature of our game, and unfortunately, there is no guarantee that there will be some unique story that will be consistent with all observations, even if we had all the rules of the game. And the fact that we don't have all the rules of the game makes it even more complicated.
Does that point to a fundamental limit of cosmological theorizing, that there seem to be these inbuilt severe limitations on what we can infer even when we've reached the final theory? But perhaps that's not what you're saying. Maybe what I'm saying is far more general and dramatic than that. But I know in philosophy of science there are these issues like the underdetermination of theory by evidence, where like even given the most extensive evidence or set of observations possible, you're still going to have multiple theories that are compatible with that evidence. What do you make of those? Are people who are worried about those kind of limitations, are those just overzealous philosophers, or is this like a real limitation on our knowledge of the universe?
Well, I mean, maybe limitations for you, but that's what makes our paychecks. So I'm happy with that. Yeah, I mean, will science stop because at some point we figured out everything? There's nothing more to be figured out, and I don't know, maybe not, but I mean, I think I enjoyed the process, and hopefully I want that for the future generations. So hopefully there will be underdetermination, and there will be kind of, there will be underdetermination, but whether it's fundamental or not, that would be, of course, that's what I would caution against, because we never know what's fundamental. There will always be new ways of seeing the universe through observations, through theory, through various insights that we've kind of learned over decades and centuries that we wouldn't have anticipated before. So whether there is a fundamental limitation, that we can never tell, but there will be limitations, and our job as scientists is to push against those limitations. And so far, I think we've done okay.
One thing I want to add is, I don't want to give away spoilers to the end of the book. I think we should read the book. But one thing is that we do talk about ways to test between different models, and some very new ideas are out there that can distinguish between some of the ideas that we examine in the book. And so some of them, one of them was actually made by one of the main critics of a model, and he was like, oh, actually, now I thought of a way you could test it, So I don't want to underappreciate the ingenuity of human beings and how clever they can be in coming up with ways of probing more and more the origin of the hot Big Bang and what might have come before. So I'm kind of optimistic that it can be done, and we do talk specifically about ways that it could be done. Of course, that doesn't necessarily mean you're going to answer every question, and there may be questions that we can never answer. So, it might be the question of whether the universe had a beginning is one we can never know, or whether it's infinitely big, or whether it's finite in size. Maybe we can never know that. But I'm optimistic. There are ways that we can distinguish between some of the models that we talk about in the book. And so there, I think, of course, for optimism.
Do you think that there is something intrinsically, scientifically unsatisfying about the idea of an absolute beginning to the universe? that there seems to be this sense, and maybe this is just me reading into things, that cosmologists have sometimes been motivated by the idea that an eternal universe is more scientifically satisfying. You don't, and like, how would we cash this out? Well, in an eternal universe, you can extrapolate your explanation of every state of affairs infinitely far back. There will always be an explanation for the universe at some stage given by the state of the universe at a prior time and the dynamical laws in place. If you reach an absolute beginning of the universe, now perhaps some cosmologists like Alexander-Vilenkin will disagree, but if you reach an absolute beginning of the universe, it seems much harder to get a scientific explication of that beginning. If you have a t=0 where everything, all of physical reality begins to exist, well, you can't really explain that event in terms of a prior physical event and the natural laws that were operating. Rather, it seems like a fundamental stop to scientific explanation. So this isn't a point about what is scientifically plausible or not. It's just a sociological point. But what do you think about that? Is there something less satisfying about a beginning of the universe compared to an eternal one from a scientific vantage point? Niayesh?
I think I'm actually have the opposite point of view on this. I'm not sure how common this is, but yeah, I think this idea of having a story for what came before is more something kind of primal in us, that we like to have stories and mythologies. I mean, we all humans like creation stories, and there are many of them, and I guess people have, whoever had the better story would have better audience. But frankly, from a scientific point of view, that doesn't seem very economical. I mean, why you have to keep creating stories after story after story? I mean, of course, we won't be able to test all of them. I mean, it's impossible to test all these things if you just keep going back and back. It seems that it's much more economical if our only goal is to explain what we observe. It's just stop things at some point. This is the beginning. We set some set of laws on that beginning surface, and then that's all. That's it. Everything that we ever observe would come out of that surface, and what came before that is irrelevant. There is no before that. That's it. That's, as far as science is concerned, that was the beginning of time and nothing else. And indeed, there are models like that. So, I mean, the two famous examples is, there is either Alex Vilenkin's or Harton and Hawking no boundary proposal, where assume that basically universe starts from just 4 dimensions of a space, and then at some point so you have no boundary, it's kind of a sphere, and then at some point it matches to 1 time and 3 dimensions of a space. But then another one, which is one I worked on with my collaborator, Kostas Iskanderis, and from a student, Best Gould and others, is known as holographic cosmology, where you basically say that at some point early, there's no time anymore, there are just 3 dimensions of a space. And you have some theory, some sort of a quantum field theory, to describe the properties of things that come out of this 3D surface, which has just a space, no time. And that's all the observables just depend on those properties, and you don't even have to ask the question of what came before. Now, maybe there was a before, maybe time emerges somehow from more deep quantum theory at that point. But as far as cosmology and observational cosmology is concerned, we don't really care about that. All we need is what came out of what existed on that surface, and all observables just depend on that. So I think personally, I think that this is much more, and if you want to go with the Occam's razor, this is a much simpler story that could explain everything we see, and anything on top of that is really not necessary.
Phil, anything?
I mean, to me, we should be open-minded about both options, right? Maybe the universe did have a beginning, but whichever one we go for, it should be based off of observations. So if the theory that says the universe had a beginning makes different observations, then we increase our credence in it when those observations come back in accord with the model. Similarly, models without a beginning are treated in the same way. So I just say be open-minded. I think both are possible, but don't be premature in your conclusion. And I think what's happened in cosmology is that these singularity theorems came out. Well, they existed before Penrose Hawking, but Penrose Hawking were the watershed moment where people really took them seriously and thought maybe this is the description of the universe. And I think that was premature. So all I would caution against is, don't jump to conclusions when, you haven't tested them properly. So be open-minded. The universe might have had a beginning, might not have. I think both are on the table, and we wait and see, if we can test these ideas. But all of them, like we do talk about models that have a beginning and models that don't in the book, and I think a lot of both options have something going for them. So I think we should just not. What do we say with this phrase in the book? Be an explorer, not a believer, I think was the phrase we used.
Mm-hmm. Yes. So I have one more question for you. It's about the style that you chose to write the book within. Rather than a kind of crisp and perhaps more dry presentations of just the scientific ideas, the models, the theories, here's what they assert, you deliberately chose a more narrative structure to weave around these ideas, to feature in the historical context, the people, the egos, the fights that are the story of 20th and 21st century cosmology. Why did you do that? Why did you feel it important to include those biographic sociological details rather than just like a more Brian Greene style of exposition where you just kind of lay out contemporary physics?
Well, I think the simple answer is it's more exciting. If you want a good book, you want to turn the page, right? If it's a sort of dry textbook, you turn the page, okay, because you've got your homework to do or whatever. Maybe, obviously you're interested in the subject, but it's much easier to turn the page when you have a narrative and you have characters that you care about, and there's conflict and drama. I think all those things just make the book more interesting. But on top of that, in our book, we're talking about science at the frontier, at the edge of knowledge. And this is where there is conflict, and this is how science is done. So people might think, oh, this is terrible. These scientists are all at each other's throats, and they're disagreeing with each other, and there's a lot of high tension and drama. But this has always been the case in science. Ever for thousands of years, people have had rivalries and conflicts. Of course, you had Newton versus Hooke, and you had the atomist school versus Aristotle, and these sorts of conflicts have always been part of science. And I think there's a worry that you might think that this is sort of bad for science, but actually it's just part of the scientific process, because ultimately I think what we wanted to say is that science is a human endeavor. So it will have all the features of our humanity, and that includes the optimism, the cooperation, but also it includes the conflict. Oh, we've lost Niayesh. I don't know what happened, but yeah, that's basically why we went for that approach. And hopefully it's just more entertaining.
Well, yeah, it was. I'll wait for Niayesh to pop back on here. Yeah, I thought this book was awesome. You really did something here. I don't know what the reception more broadly has been. I'm assuming quite positive. But this is a very well written and unique book because of that narrative, I think.
Yeah, thank you. Well, that was what we were going for. And I was certainly inspired by some other books I'd read. There was one called The Dinosaur Hunters, and it's all about the discovery of the dinosaurs, basically. And the rivalries between the paleontologists were really dramatic. And there's lots of twists and turns in that story. So, and of course, people are familiar with the rivalries between the steady state and the Big Bang. That was around, sort of between the sort of 40s, 50s, and 60s. Right. So that's a very dramatic story. And those sorts of dramas, continually play out. And yeah, they would just make it much more readable.
Well, I mean, the way you put it, it makes it up. I mean,
yeah,
it sounds very boring, but that option, yeah. But I mean, indeed, the science is, yeah. So we wanted to present science the way scientists do science, and it involves all the human things about what humans do, right? And it's not cut and dry. There's a lot of drama, and there's a lot of egos and personalities, and There was much more drama in the original version of the book, but then our editor didn't want it. And we needed to get approval from everyone. Otherwise, we might have gotten sued, or still, we may still may get sued. Who knows? But that's the nature of humanity. It's messy, but that's what we're dealing with, and it's important to understand it and embrace it. And it's vital science is vital for humanity. So it's important to understand how it's done. And if something doesn't work for it, we have to understand how we can make it better.
Well, I thought the book was eminently readable, very well written. I was most impressed by the spirit of humility which pervaded the exposition, at least that was conveyed to me. I felt like I was reading someone of a kindred spirit, because it's very much how I feel thinking about the deep philosophical questions day in and day out. And I liked the opening of your chapter 11. You said the phrase "follow the science" should really be amended to "follow the science and embrace uncertainty." Now, here at the Uncertainty Podcast, I couldn't agree more, and it honestly made me think I need to amend the tagline of my show to "follow the philosophy and embrace uncertainty." If there's any conclusion I can come to, it's that from doing these kinds of things. So, good job, gentlemen, on this book. I heartily recommend it. It's an awesome read. And so it's got 5 out of 5 stars from me. So thank you for writing it, and thank you for coming on the podcast. There it is.
All right. Thank you so much, Miles. It's been a pleasure.
Thanks, Miles. It was a lot of fun.